Alrighty. Welcome back, everybody. Hope your exam went well. I haven't quite looked at all the scores yet, but I did do a little glance yesterday before everyone had finished. Score seems overall pretty good, so I'll let you know what the average is probably later today in Discord, so you can kind of see where you are on that. Just keep in mind again, it is out of 70 something points, so take the percentage of your thing if you want to see your score rather than the raw score itself. So, of course, it'll seem shocking, but it may actually be a pretty high score. So, cool. Um, Today we're going to continue on talking about phase changes. I guess we haven't started phase changes yet, but this is technically part of the same topic relating to intermolecular forces that we had started last week. Um, we'll probably finish this chapter today. I have put your homework up for this, and it's a bit of a longer one because there's quite a bit of stuff on it, but you'll see that most of the worksheet is going to be just like, one of the pages is like 5 things you write down on the entire page. So it's going to seem long. Don't underestimate it either, but it's not as long as it will seem to be. So that homework is up. It'll be due Sunday as normal. And there's also going to be a lab simulation due this week as well. And if you want to get ahead, I suppose I also put up next week's lab sim that'll be due in a couple of weeks. So if you want to do that for some reason, you're welcome to. So that being said, if there are any questions from stuff we did last week, you can go ahead and let me know. Otherwise, we will continue on with this. So, in that case, let's talk about phase changes. So, perhaps by now, we remember the states of matter that we talk about in this class. We're going to see that we have words to describe all of these transitions. And thankfully, most of these words we are happily familiar with. When we talk about something going from solid to liquid, of course, that is melting. When we talk about liquid going to gas, that's evaporation or boiling. And perhaps the less common one for a solid going directly to a gas is called sublimation. And so that's what dry ice does. It's what water ice does in your freezer. Like if you've put ice cubes, or if you have an ice cube tray in your freezer, you'll notice over time, maybe like the day you make your ice cubes, they'll be normal size. But if you come back in a couple of weeks, you'll see your ice cubes are actually going to be quite a bit smaller than they would be normally, and that's because some of the ice is subliming into water vapor, and that freezes on the side of your freezer, and that's why you get kind of that buildup of frost potentially, depending on what kind of freezer you have. But maybe you've seen like the freezers where they have all the frost around the sides. That's as a result of sublimation in reverse. So the water sublimes, and then later it will deposit back as a solid. But we'll talk about that process in a little bit. What's important to know here is that all of these are perhaps the easier one to think of. We have a word to describe all of these that perhaps we remember from way back at the start of the semester when we talked about kind of energy and how that figures into various processes. We talked about exothermic and endothermic processes, right? or exothermic ones give off energy and endothermic ones need energy to take place. And so if we want to think about these processes as exo or endothermic, perhaps the easiest one to look at is boiling. If we wanted to boil some water, very common thing, we do it all the time, we would have to put in heat, right? You have to put it on your stove, put it in your microwave, or some other device, your kettle, or whatever, to get it to boil, right? You have to give it energy. And as a result, we're going to see that all of these are endothermic processes. So they all require energy to take place. So if you want your water to boil, you have to give it heat or some other type of energy. And so we're going to see that all of these processes, all three of these, are endothermic. And we describe these as having a change in enthalpy. Did we talk about enthalpy yet in this class? Maybe. Oh, well, we'll talk about it again. Okay, so we have not. Okay, cool. So enthalpy is what is called heat energy. That's what enthalpy is. And as we certainly have talked about delta, right? So delta H is basically your final minus your initial, right? For anything. So that's going to be your heat energy at the end, starting with your heat energy at the beginning. And so if this is big and small, that's going to be a positive number, right? If you have a large heat energy for the final and a small heat energy initially, then you'll have a positive number at the end of the day, right? And so that means more heat final versus less heat would be positive. And we're going to see that this is going to be the situation for any endothermic process. So for anything that is endothermic, we see it is a positive delta H. So we have more heat than we started with, which tells us that something has put in heat, right? You can't just all of a sudden get heat out of nowhere, right? So we have to get it from somewhere. If we're boiling water, that typically comes from a combustion reaction, or if you have an electric stove, it's some electrical resistance putting off heat, or induction uses magnetism to put out heat. And so for all of these, there's some external thing putting in heat to get your water to boil. And so as a result, we have more heat at the end than we did at the beginning, and so we have a positive delta H, which is delta H stands for enthalpy, which is heat energy. Okay, so all of these processes, if we want our ice to melt, we have to take it out of the freezer, right? We have to put it in an area that it can get energy from. So it can just take energy from the ambient air around it. But if we really want our ice to melt, we would perhaps throw it in some boiling water or throw the ice outside into the sun or something. The more energy we can give it, the faster we're going to get that process to happen. And then sublimation, again, you would technically need to put heat in, but most of the sublimation things have plenty of heat at just room temperature to happen. So it all just kind of depends on your substance. Okay. Notice that these also go from more organized to less organized in terms of kind of molecules, right? We know solids are nicely clumped together. Oftentimes they're arranged very nicely in crystals, or they may be amorphous, but we'll see that solids are typically well organized, and then gases would be the opposite. They're just kind of particles flying all over the place, zipping around. So we see that it's going to take heat energy to kind of break these bonds that hold things in an organized manner. So the reason all of these are endothermic, so solid to liquid to gas, is endothermic because we are breaking intermolecular forces as we do that. So with solids being the most organized, they kind of have permanent intermolecular forces. So if your water molecules are arranged, nicely in this lovely crystal, they're all stacked nicely together. This could be something like a solid. Whereas in a liquid, we're going to have a little bit more disorganized stuff happening. And in a gas, we're going to see we don't even have interactions happening. Oops. Wow, that's so far off the side. Okay, let's try that one again. So with our solid, we have very nice intermolecular forces happening, nice hydrogen bonds between these water molecules. We also have that in the liquid water, but they're a little bit more chaotic. And so they're kind of in various angles and moving around, so these are constantly kind of breaking and reforming, whereas in solids, they're held in place. So let's just write that. IMFs held in place. And this is going to be the true, or this is going to be true for any substance. It doesn't have to be water, it doesn't have to have hydrogen bonding. We saw that all molecules will interact together, whether that's through dipole interactions or London forces. And so everything will be similar to this, where solids will really maximize your intermolecular forces. In liquids, we see they will break and reform. And then in gases, we do not have IMFs. And so as you can kind of get from this, is that solids, you've got really nicely structured intermolecular forces. Remember, it always takes energy to break bonds, to break connections between molecules. It takes energy. So, as we can imagine, the liquid state would have more energy because these bonds are able to break, and then they reform again, but they're still able to break in the first place. In solids, they don't break. And then in the gases, they're completely broken all of the time. They don't even form. If they form, they break apart really immediately. They have enough energy, they just completely break apart. So that's why all these processes are going to be endothermic. You put in energy to break those intermolecular forces. All right, and we're going to see that energy is going to be unique for each substance. Cool. Any questions on that? Okay, cool. I guess we can just also say that this has the most enthalpy, or energy, and this one would have the least energy for solids. Okay, so let's take a look at the opposite stuff. And I'll use a different color this time. Let's use the dark blue. We're going to look at the opposite processes now. Again, the liquid-solid transition is probably the one we're most familiar with. That's called freezing. It's sometimes also called fusion. For a gas turning into liquid, that's condensation. That's what you see on your windows, or if you were to go to like a cold window and breathe on it, you see your foggy droplets kind of forming. That's condensation, so water vapor turning into a liquid. And then the opposite of sublimation would be deposition. That's a gas going directly to solid, so that's how you would make dry ice. And that's also how you get that frost in your freezer, is that's water vapor depositing as a solid. So it doesn't actually turn into a liquid, it just goes directly to a solid. Alrighty, so we're going to see that all of these ones are all going to be exothermic. These are going to be the opposite processes of what we saw earlier, where we saw, if we wanted to boil our water, we would have to put in energy. And if that gas wanted to recondense again, it would have to give off energy to do so. This is why steam burns are particularly nasty. So steam, not only is it very hot, but it will condense on your skin as it finds a place to give that energy to. So as soon as your hand or whatever contacts the steam will immediately start condensing on your hand, because the steam has found a place to dump its extra energy. So it contacts your hand is a lower temperature. Temperature will kind of move from high to low. So it will condense on your hand, releasing a lot of energy as it does, which gives your hand way too much energy, which causes the burn. So steam burns are particularly nasty, much nastier than just touching something hot, because you have all this extra energy coming in from the exothermic process of condensation. Alrighty, we're going to see that it's going to be the same scenario for freezing or deposition as well. Those are all going to be exothermic processes. If we want our ice or water to freeze, we have to take away its energy by putting it in a colder place, like the freezer or outside during the winter. And we're going to see, as a result, the delta H will be negative for all of these, meaning we have less heat than we did before. And so we will have more heat that we are going to end up with less heat than we started with, and so overall that will be negative. And so it's exactly the opposite process of what's happening here. It takes energy to break bonds, but we're going to release energy to form bonds. So if we're going from gas to liquid, we're going from no intermolecular forces to having intermolecular forces. That's going to be forming new bonds. It's going to release energy. And so the same thing going from liquid to solid. All right, so all these will be negative. What's interesting, though, is that the absolute value of delta H is the same for opposite processes. So let's go ahead and look up some numbers here. Let's see. If we just look up something for water. Okay, cool. So the delta H associated with water freezing is, what is it going to be? Okay, we're looking at 334 joules per gram. Okay. We're going to see that this is also the same amount of heat that would be associated with water melting as well as freezing. And so this is the magnitude here, 334 joules per gram. We're going to see for freezing, the delta H would be negative 334 joules per gram. For melting, it is positive 334 joules per gram. So it's the same amount of energy that would be released or absorbed depending on what you're doing. So to break all the bonds necessary to melt a gram of water, it takes 334 joules to do that. And if you wanted to remake those bonds, you would end up getting out 334 joules for that 1 gram of water. So typically you'll see just delta H is given to you as a number, but it's kind of up to us to remember what the sign is going to be. So it depends which process you're looking at. This delta H specifically would be written as delta H fusion for water. You would see this given as something like this. And it would be up to us to understand that we would use this delta H fusion when we're talking about melting and freezing. So we use this particular constant for melting and freezing of water. Every substance has their own delta H fusion. We're going to see that there's another one that's pretty common called delta H vaporization. And if we're looking at its value for water, we're looking at about 2,230 joules per gram. You don't need to memorize these numbers, by the way. They would be given to you if you ever need them. But this is what we're looking at here. So we would use the fusion for melting and freezing. And we use vaporization for boiling and condensing. Let's try that again. So that's liquid and gas. This is liquid and solid. All right, so you'll often see these ones written. Sometimes you'll see them as delta H FUS and then delta H VAP. So you might see them abbreviated like this as well. Okay, and this tells you how much heat energy is required to freeze or melt or boil or condense. So lots of fun vocab words right there, right? So let's just kind of write that out. So delta H tells us the amount of heat energy associated with changing the state of matter of a given amount of substance. And so delta H fusion is for solids to liquids and vice versa. Same value, but just different sign. And then delta H vaporization is for liquid and gas transitions. So boiling and condensing. Again, the value is the same. You just change the sign depending on which way you're going. All right, typical units for delta H. Will be some sort of energy unit over an amount unit. we're going to see that we typically have two energy units that we're going to deal with. We will use joules. That's a pretty common one, as well as calories. All right, and just so you know, 1 calorie is 4.184 joules. Just so you know. And also, 1 calorie with a capital C is 1,000 calories with a lowercase c. Isn't that quite silly? You might see this as kcal as well. So if you look at your nutrition labels for something, let's see, do I have anything around here? No, but if you look at a nutrition label, it will have calories with a capital C. It's something that's used for nutrition. It's not something that we're going to really use in chemistry. We'll use lowercase 1, the regular calorie. But just so you know, if you were to read your nutrition facts, if something says it's 100 calories, that's the big capital C one. So it's really a million or 100,000 small calories. All right, so this one is for nutrition. All right, and then sometimes you'll see it written as kcal, which is 1,000 calories, right? Kilocalories. If you go to Europe or other areas, instead of putting calories, they put joules or kilojoules as their energy value for the food. So these are kind of the typical units we'll be using for energy. And then for our amount units, we will typically either use mass in grams or kilograms or moles. Those are kind of the two that we'll use for looking at these. So the first one that I gave you joules per gram. You could be given calories per gram. You could be given kilojoules per mole. You know, there's all these different units we can use here. So any kind of combination of these is pretty common, honestly. Alrighty. Enough of this. Let's actually do some work with these. So let's take a look at this. How much energy, aka heat, is needed to boil 250 grams of water? And we'll go ahead and put delta H fusion was 334. Delta H vaporization was 2230 joules per gram. Alrighty, so if this is a question for us, how much heat is needed to boil 250 grams of water? We have a choice to make here. We have to first select which delta H is going to be the one we're going to want to use here. And then we also need to consider the sign of the delta H that we're going to use. Yes, so definitely we have the mass of water, 250 grams. We're good. Looks like our delta H's are already in something with grams as units, so we don't have to worry about it. Indeed, so we'll use the delta H vaporization here. So we're going to use this one because we're dealing with boiling, right? So we know that our energy here, Q, remember, is energy. We talked about that a long time ago. That will be 250 grams times our delta H value, right? We have to also consider, is delta H going to be positive or negative here? So right now I'll just write it as both. So we're boiling the water. Does that mean we're putting in energy or we're getting out energy for doing this? Well, if we want to boil it, we have to put in energy, right? So that means that delta H should be positive overall. Yeah, we're adding energy, so it should be positive. All right, so all we have to do is multiply these numbers together. And just like any other unit conversion, we'll see that some units will cancel out. We'll be left with joules. So if we do this math, let's see, 250 times 2230. Looks like we're going to need 3 sig figs overall. So that brings us to 558,000 joules. Or if we wanted 558 kilojoules. Either way, depends whatever, unit you're asked for. So if I asked for joules or kilojoules. We did use the grams of water. It's right here. Yes. So that's why. So delta H vaporization is the heat for a certain amount of substance. So it tells us how many joules for every 1 gram. So if we have 250 grams, we would have to multiply our delta H by 250. And yes, of course, we'll cancel out the grams as a result. So this value comes in down here, and this delta H vaporization goes in right here. No worries. There was no bad that was committed. So yes, yeah. So these are specific for each substance. So we can do it for a different substance. Let's see. I have to look up these values though. Let me look up its data page real quick. I don't need any of these things. Enthalpy of formation. Fortunately with these, there's often so many. Okay. There we go. The data page. Okay. So let's talk about another one. Okay, here we go. So how about this one? To freeze. So is this going to be given in moles? Yeah, we'll do it with moles. 2.28 moles of acetone. Let me get these. Enthalpy change of fusion is 5.7 kilojoules per mole. And delta H vaporization is 95. I'm sorry, I wrote the wrong number. 31.3 kilojoules per mole. Alrighty, so here we have different units, right? Previously we had joules per gram. This time we have kilojoules per mole. No problem. Doesn't really matter. Acetone, by the way, is a pretty common solvent. You can go to Home Depot, pick some up. It's used to dissolve a lot of various things, so like various adhesives or I don't know if paints are necessarily dissolvable by acetone, but styrofoam will dissolve in acetone. Nail polish will dissolve in acetone. It looks like this. That's what acetone looks like. Trigonal planar, of course. 120 degree bond angles. All of our favorite things here. Exciting stuff. Okay, so anyways, let's see. How much energy to freeze 2.28 moles of acetone? Well, let's go ahead and take a look at some of these numbers here. So we're dealing with freezing. So we're going to want to use delta H fusion, right? Fusion deals with freezing and melting. And so now we have to remember, is freezing exo or endothermic? May not be so obvious, but if we look at the opposite one, to melt something, we have to give it energy, right? So if you want it to freeze, we have to take away its energy, meaning that freezing is exothermic. And so we're going to see that we're going to use a negative value this time. So we have our moles, but this time we have a negative value, which is okay. Q is allowed to be negative. All right, so if we go ahead and do this math then, 2.28 times negative 5.7, you get negative 13.0. Unit, of course, will be kilojoules. Moles will cancel out, just like before. All right, and so just this negative sign, oops, this indicates the heat that is released. If it's positive, that would be heat absorbed by something. So exothermic process heat is going to be released. So we're going to see that we end up with a negative value for Q, which is okay. We have less energy than we did before. We got rid of extra energy. So we're okay there. All right, any questions on this so far? So just remember, you could be given any kind of unit here that I wanted. So you would want to be, if I were to give you a problem like, how much energy to boil, I don't know, 200 moles of water. And I gave you that delta H vaporization was 2,230 joules per gram. We would have to convert some units, right? We could do two different options. Probably the smartest one would be convert this to grams of H2O and then use it with your delta H. Or you could take your delta H and convert it to joules per mole instead, but that's a bit harder to do. But it would be the same process. So hopefully we'll remember how to go from grams to moles and vice versa. Remember, that is a conversion factor called molar mass. And for water, that's 18.02. Just adding up an oxygen and 2 hydrogens. If we wanted to do this math, we could do it. We would say, okay, we have 200 moles of water. We would use the molar mass to go to grams. And then we can use our delta H. And we're going to see that our units should always cancel out, just like with any other unit conversion. You didn't believe me when I told you unit conversions were the most important part of this class, right? And so that's all this comes out to be. So delta H is just a conversion factor between energy and amount of substance. So that's all it is. Nothing terribly new here. Let's go ahead and do this, by the way. 1802 times 200 times 2230. And we get, oh my gosh, 8 million. 8.04 megajoules. Yeah, quite a bit of energy. So just be aware you can be given all sorts of different units. So just make sure that doesn't throw you for a loop there. Alrighty. Right, let's look at another thing here. Phase change diagrams. Oftentimes you'll see a relationship between heat added and the temperature of a substance. We can use water for this case. Water is nice because we know its boiling point and its freezing point, right? They're easy numbers. However, if you're given a different substance, they would have different boiling and freezing points. But we'll see that these graphs typically will follow something that looks like this. And so there's some kind of important points on this graph here. Let's just kind of label these. So that's point A down there, B, C, D, E, F. So if this is water, what state of matter of this area between A and B? If this is water. See if we can interpret this graph. Not quite. It's one state of matter only in that area. So if water is less than 0 degrees Celsius, it should just be ice, right? It's just solid, exactly. So this area here, let's see, let's use purple. This part, it's entirely solid. And we're going to see between C and D, we're going to have liquid water. Right? So that's water or between 0 and 100 degrees Celsius. And then way over here at the very end, we have the gas above 100 degrees Celsius. And this is kind of where you were going here. Between these two sections, we actually have both states of matter at once in those flat areas. What's interesting and perhaps a bit unusual is that while the ice is melting, that's the transition from B to C, the temperature does not change. All the energy goes into delta H. So breaking those bonds between them. So all this area at B to C there, where it's ice and water at the same time, ice water, there's no temperature change. It will be 0 degrees the whole time. So if you take ice water and you have a thermometer at home, you'll see that it should be 0 degrees Celsius or 32 Fahrenheit the whole time. As long as you have both ice and water in there, the temperature will be 0 degrees Celsius. And all of that energy is going into breaking intermolecular forces instead of making things move faster. So that's why we're not going to see any temperature change there. What's easier, perhaps, is boiling water. Also does not change. We know boiling water takes a very, very long time, right? You can put it on the stove and, forget about it, and it'll take a long time to boil, right? Hours and hours to boil all the water away. If you put your thermometer in, once it starts to boil, it should be about 100 degrees. And if you come back an hour later, it'll still be 100 degrees, even though you have the stove on the whole time. All that energy is going into breaking intermolecular forces. And as you can imagine, solids and liquids are kind of similar together, right? So we see that that's going to be a kind of smaller part of this graph. But liquids and gases are very different, and so it takes a lot more energy to break those than it is to go from solids to liquids. So that's another thing I guess I should write down here. More energy is required. So typically your delta H vaporization should be bigger than your delta H fusion. Just as a result, it takes more energy to boil water than it does to melt it. So we don't have to worry about that. Alrighty, so we have seen... Oops, this one's vaporization up here. That if you wanted to calculate the energy required for these particular steps, we would use the delta H's, right? If it's boiling, we would use delta H vaporization. If it's melting, we would use fusion. But what about this energy? What the heck is this Q? Well, we can see here on the graph, those areas that we had delta H's, B to C and D to E, those had no temperature change, right? So all the energy goes to breaking bonds instead of raising the temperature. However, once we're in the liquid state, that last bit of ice is melted at point C, all our energy goes into now increasing the temperature, so making things move faster. And perhaps we remember way back when we had our dear formula that deals with temperature change and heat, right? Way back when we talked about this. And this is how we would calculate any energy change that would happen between just one state of matter at a time. And so it's using the specific heat capacity of that substance in that state. So remember that C is different for every state of matter for a substance. So for liquid water, it's 4.184 joules per gram degree Celsius. For gas, it's, I don't remember, but it's something smaller. For solid, it's also probably smaller. But it's different. Each substance will have 3 different specific heat capacities. And so they're all different from each other. Alrighty, so let's kind of just summarize this section here. So if you are calculating the energy for a phase change, that means you're changing your state of matter. You use delta H. Where M is either your moles or your mass, whatever your delta H units need to cancel out. If you are calculating the energy for one state of matter, that's when we use MC delta T, the MCAT formula. And so, if we were to just kind of look at a graph here, we're not going to necessarily calculate everything, but we could if we wanted. Let's take acetone again because I already had its stuff up, all of its constants. Let's go ahead and look at acetone. Let's see. Its delta H fusion was 5.7 kilojoules per mole. The fusion was, or vaporization, 31.3. We have its specific heat capacities. At solid, that's 96 joules, per mole degree Celsius. Its liquid heat capacity is, where did it go? 125.5 joules per mole degree Celsius. And finally, its gas constant, specific heat capacity, is 75 joules per mole degree Celsius. Lots of constants here, right? But we're not done yet. Just to throw this out here, we also have, let's see, where is its... we also need to know its boiling point and freezing point, right? Its melting point or freezing point, whichever one you look at it, is negative 94.7 degrees Celsius. Right, its boiling point is, where are we? 56.05. Okay, we have a crap ton of information here. Wow. Lots of stuff. But we're going to see that those 5 constants there would be used if we were to calculate the amount of energy required for one specific portion of a similar type of graph, right? Let's say we are going from, let's take, we'll make this easy, 100 moles from negative 100 degrees to 100 degrees. Let's just look at what that's going to look like on a graph. So, if we're looking at what we did before, we saw that on our graph, we should definitely have our melting point and boiling point, right? For water, that was 0 and 100 degrees Celsius. For acetone, those are different values. Right, every substance has a different melting and boiling point. So let's say this is negative 94.7, and this is positive 56.05 degrees Celsius. So that's the boiling and freezing points that I've just put on the graph here. If this problem says we're going from negative 100 to positive 100, we know we're going to start at negative 100 and we're going to end at positive 100. And we're going to see the shape of the graph is going to look just the same as it did before. So we start at negative 100, we go up to negative 94.7, stay there for a bit. We go up to our boiling point, stay there for a bit, and then we go up to our final temperature. So graph looks exactly the same. Right? And it's going to be the same as it was before. So we have solid, solid and liquid, liquid, liquid and gas, and just gas. Just like before. Nothing new here. And as you can see, if we kind of label these as we did before, we're going to see all of these lines would be a separate calculation for Q. Isn't that exciting? All of these lines here are their own Q calculations. So if we really wanted to find the entire amount of energy to do this, we could. It just takes a very long time. It's just a bunch of calculations. We would see that we would need 5 separate Q calculations to find the total energy for this. Which is just bonkers, right? We're not actually going to do that, don't worry. But we can kind of figure it out. I just want us to figure out what to use when. That's the important part here. So if we're looking at AB, that's where it's solid only. Anytime we're dealing with just one state of matter, we use our MCAT formula. So if we were looking at that one, we would use M, the C for solid, and the delta T. If we're looking at B through C, that's where it's solid and liquid together. At that point, we would use delta H fusion, right? For C to D, that's where it's all liquid. We would use our specific heat for the liquid. For the next one, we would use our vaporization. And then finally, we would use our gas specific heat capacity. And for all of these, M would be the moles, right? Because all of our stuff here is given in per mole, so we don't have to worry about that. But one last thing to note with this is these delta T's are troublesome, right? If you want to think what's the delta T here, well, that's just 56.05 minus negative 94.7, right? That's the difference in temperature. If we're looking at this delta T, it's 100 minus 56.05. All right, we're just looking at the graph here. So when it starts boiling, it's at 56 degrees. We're ending at 100 because that's what the problem says. And for this one here, for the solid, we would start at negative 94.7 minus negative 100, and we would get whatever we get there. And so we're going to see there's a lot of stuff we can do with this sort of graph. I can make your lives hell by using something like this and make you calculate these forever. But I won't, because I don't want to grade that. That's what it comes down to. But now that you're completely overwhelmed, here we go with our crazy face here. The whole point of this is just showing you how you could do something like this. We're not going to do it. It's something you'll do in 111. But if you wanted to look at the steps for this, I think your homework worksheet will have you do 3 of these. And it'll walk you through each one. So it'll do it step by step by step for you. But if you wanted to find the whole thing for an entire phase change, you would need 5 different Qs. And then you would have to just add them all up at the end. So now that our minds are blown and we have rotted our brains away, not only with the exam yesterday, but now with all this math, any questions? We're going to see, you'll have plenty of practice on your homework with doing these sorts of things here. So on your exam, of course, you will not have to ever do a 5-part problem like this because it's multiple choice. I can only ask you one little bit at a time. So it's really the kind of key points here are what state of matter are you at a given point on one of these graphs, and what would you use to calculate the Q at that point or at that transition. That's the kind of takeaways here. So if you can do that, that's all you need to know. So if I'm asking you, okay, what do you use at DE on this graph, well, you would say, okay, we're going to use delta H vaporization. That's what I want you to be able to do. All right, and to also understand that that's both liquid and gas at the same time. There. All right, we are out of time for today, so mull this over. Come back tomorrow with questions, and yeah, we'll continue on. So enjoy your Tuesdays, enjoy your brain recovery periods, and I'll see you tomorrow. Yes, it's a good idea. There's a lot of information for this one, so cool. See you all tomorrow.